Hi, that's me, Marcy, a computer science major from the University of Central Florida. And that's Dr. Karima Weiss and Islam, my PhD mentor. I worked in a lab at the University of Florida this summer to create an all-optical BMI for rodents and to study brain plasticity. A brain-machine interface, also known as a BMI, provides a direct communication between a brain and an external device, often used for assistance to help with disabilities and efforts to regain one's functionality and autonomy. Here is a clip taken from CNN that depicts a paralyzed man connected to a BMI that allows him to move by using a neural decoder to translate brain signals into commands. Now, optogenetics uses light to stimulate neurons that have been genetically modified to express ion channels that are light sensitive. Calcium ions are naturally present in the brain. They can be fluorescently tagged and are directly correlated with neuronal action potential firing rate. Through microscopy, they can be imaged. It's important to note that rats have whiskers that can send electrical messages to the brain when it comes in contact with an object. The rats in our experiment were injected with a non-lethal virus containing the DNA encoded for both proteins using calcium imaging and optogenetic stimulation. There are two main parts of the brain we are focused on here: the sensory cortex, VS1, and the motor cortex, VM1. The sensory signals received from the whiskers are processed in VS1. When the rat whisks or thinks about whisking its whiskers, these signals are visible in VM1. With optogenetics, the use of fiber optic cannula BMI implants, we provide stimulation to VS1 in order to induce an artificial sensation. When we provide stimulation, we want the rat to associate that feeling to know it should whisk its whiskers, or at least think about it. This is our behavior box setup, where we behaviorally train them while monitoring their VS1 and VM1 signals as they move freely. Here is a draft of our final setup, where the rat will stand on a pipe that is connected to a robotic arm and will have to modulate the VM1 signals to move it from left and right to reach the reward. This fiber is connected to the rat's BMI implant, where we can stimulate and image the targeted regions. We use LabVIEW graphical programming, a new programming language I learned, to communicate with and to program National Instruments MyRio to automate the imaging. This research can lead to many applications, but mostly to aid the disabled in areas such as prosthetics. We envision that with this research, we can engineer clinically viable brain-machine interface systems to restore, augment, or repair damaged neurological function, such as hearing, sight, and movement.